In this course, you have seen a lot of different kinds of uses of LLMs. And today, I'm going to emphasize the use of LLMs as a tool of scientific and mathematical discovery. And in particular, there's going to be an emphasis on the ability of LLMs to discover abstract concepts and how this can accelerate these discovery processes. Okay, so let us dive in. Let us start with the problem of mathematical discovery. This is, of course, one of the grandest challenges known to humanity. Now, how does the process of mathematical discovery look like? There is the first, the process of modeling, where you are getting inspired by some sort of a real world phenomenon and then modeling it in terms of a variety of definitions and concepts. Now, once you have a set of definitions, at that point, you may want to conjecture various properties of these definitions. And then these are, potentially candidate theorems and lemmas. And then there is this process of rigorous reasoning where you are actually proving these statements. And this process is for human mathematicians intrinsically social. You are convincing each other about the rigor of your reasoning and the value of your conjectures, right? But this process just continues in this sort of an iterative loop. So you may see proofs and counterexamples, and these may influence your models as well as your conjectures, and this process just goes on, right? That's how that's the history of mathematics. Now, the dream of the field of AI for math is that you want to automate substantial pieces of this process. And as a result, you want to accelerate this process even more. You want to be able to discover new kinds of math, and this includes settling known conjectures, but also potentially coming up with new conjectures. And then there is the setting of natural sciences. That is also going to be something I'll cover in this lecture. And here, unlike in math, you are engaging with the real world. There is this process of theory building where you're coming up with hypotheses about the universe, and then you are using these hypotheses to design experiments, and then you are experimentally validating them, right? And this experimental validation process creates new data, and then this data leads to new kinds of theories, for example, by refinement of the existing hypothesis, or in some cases, you may want to just come up with entirely new concepts and new predictions. So the ambition of the area of AI for science is to automate hypothesis generation and experiment design. Now, the key ideas in the areas of AI for math and AI for science at this point are that, number one, search is a really powerful concept. And so we want to imagine these spaces of hypotheses, conjectures, and proofs and systematically search them. Now, this is, of course, a very massive space. There are all these potential statements about various mathematical objects, and there are all these hypotheses that are possible in the universe. And this space is, clearly infinite. Now, how do you explore this space in a tractable way? Well, you use prior knowledge to prioritize directions of search. And that's also how humans proceed. We don't just do discovery in a vacuum. We read existing papers, and sometimes we incrementally advance on them, and sometimes we make a big leap. But that prior knowledge is always of value. But then also, we learn from experience how and how not to do this sort of exploration. You find out that you made certain choices while building your theory, and then you find that this just didn't work, right? And that's experience for you. And then you use this experience to potentially take completely new directions. And then another piece that is very important, has been very important to the history of math and science, has been to discover abstract concepts and tools. So for example, the idea of calculus that really sped up the progress of science after it was invented. Similarly with algebra and really all major branches of mathematics came from the need to abstract some sort of real world process. And then the value of these abstractions is that they speed up both this process of exploration and also this learning process that I previously mentioned. Now, if you think of it, LLMs bring something to the table regarding each of these criteria. So for example, if you're doing a search in a very large space of potential scientific hypotheses, an LLM has inside it a lot of knowledge about what sort of hypotheses have historically tended to work in science. And so this knowledge can potentially help you direct this search process. And then also, in this course, you have seen examples of LLM agents, and in this class, you're going to see more of this. So these are systems that contain inside them LLMs as modules, but they're also interacting with the world and they're learning from experience. And this experience is gathered as data and then often stuck into the prompt, but sometimes you can even do reinforcement learning or other kinds of modification of the LLM's weights. But the point is that there are all these established methods for doing learning combined with the use of language models, and that is something that we can exploit here as well. Now, the use of LLMs for abstraction, this is something that's not well explored yet. This is a really new idea, but I'm going to give you some evidence as to why there might be a lot of things going on here. And there is certainly a lot more to be done about the use of LLMs in constructing new concepts and new tools. So I think that LLM agents have tremendous promise in mathematical and scientific discovery. And the reason is that so far as all of these ideas go, LLMs have a potential to contribute with regards to each. So this may all seem somewhat abstract. So I'm going to now jump into some concrete results. And this lecture is divided into two pieces. In the first part, we are going to talk about AI for mathematical discovery. And then in the second part, we are going to talk about AI for scientific discovery. And in each of these cases, I'm going to show you some LLM agents built using quite different algorithms. But we'll see that these agents realize many of these ideas that we talked about in the previous slide. Okay, so let's talk about AI for math. Over the last few years, there's been tremendous interest in this field. Here's Terry Tao from 2023 talking about how AI from that year can already generate suggestive hints and help with the mathematical process. And he predicted that by 2026, AI can become a trustworthy co-author in math research papers and in other fields as well. Now, 2026 is not yet here, but I would say that this prediction seems very plausible as of now. Now, in terms of concrete systems, O1, when it was introduced, one of the highlights was that it did really well in various competition mathematics problems. So here is a plot. It shows how O1 does compared to GPT-4o. And as you see, accuracy in this particular competition, AIME 2024, has gone up very substantially. And then, of course, last year, my colleagues at Google DeepMind, they built this system that achieved silver medal level performance at the IMO. And you've already heard a talk about that in this course. So I'm not going to go into further detail or too much more detail about that in this talk. But you know that it's impressive, and it uses a lot of very impressive machinery. Now, one question that I think is important to ask is that, is it all going to be done just with LLMs? In other words, do you need any sort of additional machinery that combines LLMs with, for example, actions? This is really the characteristic that distinguishes LLM agents from just basic LLMs. And so I would say that there are certainly still believers in the potential of just LLMs alone to do everything after being trained on language. But I am personally a little bit skeptical about that possibility. Now, that said, one must admit that over the last couple of years, just LLMs have come a long way. So here is the picture of how you train an LLM for these sorts of mathematical settings. So you're going to start with a pre-trained LLM, then you're going to train it on math-related web docs, and then problems with step-by-step solutions, problems with tool-integrated solutions, and so on and so forth. And then ultimately, you have this LLM that can use, for example, Python APIs, and that can solve math problems. And this has, again, as I said, come a long way. So for example, here is a problem from the Putnam math competition from last year. And O1's response on this problem is actually very reasonable. And as these systems are getting better and better, it seems like they're solving more and more problems that are of this nature, that are similarly hard or harder. But that said, there are some fundamental weaknesses of this neural-only approach that you'd get with just a basic LLM. And the reason is that, or one fundamental reason is that there is this issue of data scarcity. In order to do rigorous mathematical reasoning, not just computing answers to well-posed questions, you need to have a lot of high-quality traces of mathematical reasoning, or alternatively, you would need high-quality reward functions. And this is difficult to get just with human-produced data beyond high school or competition settings. And then a second reason, fundamentally, is that natural language reasoning is hard to verify. And this is something that is a fundamental weakness of this language-only models. And there are even settings where you can apply this sort of mathematical reasoning, where, for example, when you are doing mathematical reasoning about real-world systems, and the behaviors of these systems have real consequences. So edge cases are really critical. So in these cases, you want your mathematical reasoning to be really robust and rigorous. And unfortunately, language-based, purely neural mathematical reasoning tends to not be this way. And so it is entirely possible that scaling is going to solve all of these problems. But as I said, I'm a little bit skeptical about this. So in this talk, I'm going to demonstrate an alternative strategy, which is similar in many ways to alpha proof, which you saw previously, but which is more of an LLM agent approach that is an alternative to this sort of purely neural, purely language-driven kind of model. So this alternative involves formal representations, just like in alpha proof. So there's an entire literature that is building up that follows this kind of strategy. And so here, what you do is that rather than just operating in this space of informal problem statements and informal solutions, you'd be first doing what is called auto-formalization. So you're going to go from the informal statement to a formal statement in a language like Lean or Coq or Isabelle. And Lean in particular is what is used for alpha proof. But there are other frameworks like this as well that have a very long history. Now, the appeal of these sorts of formal frameworks is that a proof can be written in a step-by-step way, just like code. And not only that, a proof can be checked. You can check if a proof that you have written in this formal language actually implies a certain property that you started out with. So this theorem that you started out with. And so the idea is that you would then, in the second phase, take this formal problem statement, and then you'd be feeding it to a neural prover, which is going to come up with this sequence of steps, which are also called tactics, these rules that you apply. So these are tactics, and you apply them one by one, and then at the end, you get to this QED stage where you have nothing left to prove. And so that's how this process would work. And the advantage here is that if you think of the verification challenge that I mentioned earlier, where you want to check whether a claimed proof is actually a proof, this is something that you can establish relatively easily using a proof assistant, right? And in terms of the data issue, so the appeal of this kind of verifiability is that during training time, you can synthetically generate a very, very large number of candidate proofs. And then you can immediately get feedback on whether or not these proofs are correct. So this turns this difficult problem of proof into this kind of a game playing task, which you can approach with really a version of reinforcement learning. And this is what, for example, alpha proof did. Although I'll show here that you can also take a more LLM based approach to this problem. And in fact, you can build up on these pre-trained language models and only have a pretty thin layer on top of that. And that still does quite interestingly well. Okay, so just to go into a little bit more detail about these formal representations, even though you may have seen this in the alpha proof lecture, I'll just quickly recapitulate this. So here is a theorem that let's say we are trying to prove. And what this says is that if x is even, then x squared is even as well. So the theorem statement over here says that x is a natural number, and then it says that x being even implies x squared is also even. So modulo 2, it's the remainder is 0. So now, in order to prove this, you're going to apply this sequence of tactics, as I said previously. Now, it's important to note that the system, the proof assistant, it has a certain state that depends on what the original theorem is and which tactics you have applied so far. So for example, in the beginning, you would have a state that looks like this. Now, just to spell this out, what this means, it says that there is one goal that you currently need to prove. And that goal is that under this context, which is that x is a natural number, this is the variable that you're allowed to use. And then this symbol turnstile means that this is what you need to prove. So this is basically the theorem that you're starting out with before you have applied that tactic. Now, you have the state, and then you apply the tactic, which is, you can think of it, if you're thinking of this as a reinforcement learning setup, you are applying an action. And so you apply that action, and that leads to a new state. And then this state here looks like this. So this intro tactic, what it does is that it introduces this new hypothesis, which over here now says that, okay, let us assume that x is even along with, x is even along with x being a natural number. And this property that x is even, we are going to give it a name, h. And then under this context, which is really like, you have now declared a new variable which has a certain type attached to it. So now you're trying to show that this x square is even as well. And then you apply this next tactic, which leads to another state. So these tactics are written by humans, and they encode various rules of simplification in mathematics. And so what you're really doing is that for each of these rewrite rules that you're applying, the state is changing. So for example, now the state has changed to you showing that, if so this x modulo 2 times x modulo 2, the whole thing modulo 2, that is equal to 0. And then the next rewrite is going to simplify this. And then finally, you will end up with, 0 equals 0, basically. And at that point, you're going to hit QED because your goal will just disappear, right? So each of these rules you can think of as simplifying the state. And then at the end, ideally, you want to end up in this state where there are no open goals. And at that point, you can end the proof. So that's what these formal proof assistants look like. Really, they're state machines where you have the proof state, and then these actions, which are these tactics, and then they lead to a new proof state. And your goal really is to find a sequence of tactics that take you from this initial state of the prover to this QED state where there are no more goals to be discharged. Okay. So now let's talk about the two phases that I mentioned previously. The auto-formalization phase is something like this. You're starting with this informal math statement. There exists an infinite number of primes, and then there is this proof of this as well in natural language. And now you are applying your auto-formalization model. And later, I'll talk a little bit about how this could be done. But the version 0 of this would be that you throw a language model at this informal statement, and then out comes this formal theorem, right? And so this one is in lean. Now what this says is that, well, I won't read this thing in detail, but maybe I can read the theorem statement. It says that, so for all n, there exists a p such that p is greater than equal to n, and then p is also a prime, right? So that's how you establish that there's an infinite number of primes. And then the rest of it is the proof. So then let's assume that you have done this auto-formalization. You have a formal statement of a theorem, and now you're trying to prove it. So previously, I showed you that there are these tactics, these simplification rules that you could apply. But now you can imagine a search problem where at each state, there is a set of potential tactics that you could apply. And this leads to the creation of a search tree. And then your goal is to basically find a path in this tree that ends up at QED. Now, of course, the complexity over here is that at each point, you can have a very, very large number of potential branches in this tree. And then also this tree can be quite deep, right? Because if you're talking about really advanced mathematical theorems, you could end up with proofs that are thousands and thousands of lines long. And so this is a far harder problem than any game playing problem that we have been able to solve so far. So it's remarkable to see the kind of progress that has already happened in this task over the last few years. Now, alpha proof, of course, you have already seen. You've seen this picture. There's this formalizer network that does this formalization into formal problems. And then the solver network, it tries to generate these formal proofs. One big insight was that even misformalized problems are still helpful for learning. And this sort of proof, the solver network, this is being trained with RL. And then one big insight was that you could complement RL training with test time RL. When you are actually doing the IMO or any other, solving any other math problem, you could generate, you could basically do this sort of test time RL on that. But again, you have seen all of this, so I'll move on. The approach that I'm going to talk about today, this is called COPRA. This was published in a paper at the Conference of Language Models last year. And this is led by my PhD student at UT Austin, Amitaush Thakur. Now, this is the overall picture of COPRA. It still has this view of interaction between an LLM that is predicting the proof steps and the actual prover that is executing the step that is proposed by the LLM and then giving you a new state. However, the difference is that while AlphaProof does this sort of advanced reinforcement learning for training, so here you're just taking this sort of an LLM agent approach where you have a frontier LLM, and the frontier LLM is being provided the proof state and some information from the history of the search so far. And then it is making a prediction as to what's the next step that you should take. And then you are taking that step and you are executing it. And then you are getting back a new state of the proof. And then this process is continuing, right? Now, one important thing is that there is an external search that is going on, a depth-first search. And then inside that depth-first search, you are doing all this, right? But it is fundamentally different in the sense that everything is in context. There is no actual adjustment to the way it's happening. But what is interesting is that even with a relatively small amount of compute, this approach was still able to do quite well. And so I think that this strategy has a lot of long-term promise. For one, because it immediately leverages advances in LLMs. As, for example, you go from GPT-4 to, O1 to O3 and to, maybe someday GPT-5, then you're going to immediately leverage those advances. And it also has this ability to integrate natural language and formal language reasoning, because ultimately you are just using an LLM to generate the proofs in the formal language, but at the same time, the LLM has the ability to do natural language as well. So this is something you can benefit from. And I'm going to show concrete examples of this in a little bit. Another thing is that this strategy is also applicable even if there is no corpus of training problems. Now, one of the challenges in doing AI for math, once you go outside of settings such as math competitions, is that you're really trying to solve a new problem, right? So if you're a math researcher, you're trying to solve a new problem that by design is quite different from the problems that a lot of other people have solved previously. So in such a situation, it's a bit challenging to create a corpus of training problems and then do training of an RL agent. However, with an in-context learning agent, the appeal is that you can still use it. The LLM has inside it a ton of prior knowledge, and that knowledge is something that you could benefit from, right? And the LLM can, for example, bring in knowledge about related problems, even though it's not been explicitly trained on them beyond the pre-training stage. And in the longer run, of course, the two approaches of in-context learning and explicit training, these are not incompatible. So you could imagine the in-context learning agent being used to generate a lot of different traces by interaction with the proof assistant, and then you could use them for doing fine tuning. Now, one question that you may have over here is that, well, so do I really need to even have lean in that case? Couldn't I just rely on, the LLM alone? And I would say that the difference here is that this interaction with the proof assistant is still providing, a very strong form of grounding. So for example, if you take a step predicted by the LLM and then you find that this is actually an invalid step, you're going to get that feedback right away from the proof assistant. And you can take that feedback and you can then stick it back into the prompt of the LLM. And then you can ask it to continue, and then hopefully it'll learn from its mistake and carry on, right? So in the long run, it's possible that once you have generated a very, very, very large number of traces via interaction with the prover, maybe you have fine-tuned your LLM on all this data, and then the LLM is progressively getting better and better, and there is a point beyond which it just doesn't make any mistakes with this kind of proof. Maybe we'll get there someday, but we're still pretty far away from that possibility. So at least as of now, I think that this sort of interaction between LLM and proof assistant is still extremely valuable. Okay, so here is this Copra system in a little bit more detail. So what is going on here is that you're starting with a formal theorem, but you could also have some informal hints. You could imagine bringing auto-formalization into this picture as well, but we didn't. And so the first step is that you create a prompt based on the statement of the theorem. And then you feed it to a frontier LLM, and you just ask it to generate some potential tactics that would be of interest. And now you do the your model has predicted a set of one of the actions or tactics in this case, and then you parse that tactic because it will be in the form of text. So now you parse it into a structured format, and then you just execute it via the proof environment. And this could be lean or coq or isabel. And then after you do that, in the lucky case, you already hit QED, and this is all done. But if you fail, if this tactic is invalid, or there are still some open goals that you still need to resolve, in that case, you get some feedback, and then you augment the prompt, and then backtrack if needed. And then we also have this retrieval phase over here, which seemed to add to the performance of the system. And here you are also able to query a lemma database and bring in some relevant lemmas and then add it back to the prompt. And this process just continues over and over and over again until you have resolved the original theorem, or alternatively, you have timed out. So here's the prompt of the system in a little bit more detail. So here, as you see, there is this serialized proof state. And here you have, what is the goal that you still have to prove, and what are the hypotheses that are being made. So over here, for example, the hypotheses include, these are the assumptions you're making, right? So this includes X being of type natural numbers, and then also, X being even. And then you have the goal, which is X squared modulo 2 is equal to 0. We also have this information about the last step. So the way to read this is that from left to right, you are looking at successive queries to the LLM. So the first column over here, this includes information about, what is the first query that you're making. So the first thing that you have done, so let's say that you already have made this decision that you're going to have this intro H tactic, right? So that's what created that hypothesis, X squared modulo 2 equals 0. So then this is the last step. This is stored in a stack and fed as part of the prompt. Then at this point, there has been no error. So then, you get this response from this LLM after you feed this information that the next thing that you should do is RWH. And then now if you try to execute it, you might get, an error message because a rewrite tactic failed. And then, this information, this error feedback, you send it back to the LLM. And then that's the next query. You say that try again, LLM. And then the LLM says that, OK, let's try apply nat.mulmod right. Now, the details of this tactic doesn't matter. It's something involving modular multiplication. But the point is this is also wrong. So then again, at the next step, you get an error feedback, error message, and this is something you stick back into the prompt, and then you make a query again. And now it says, oh, let's try this rewrite with nat.mulmod. And yay, this time it works. So now you see that the interaction result doesn't have any error message in it. It's a success. And so, so this is now put into the stack. And so the last step, as you see, has changed. It's now rw nat.mulmod. So now you're going to try to generate the next step. And then this time the LLM generates this RWH, right? And so this is how this process is going to continue. In a nutshell, you may query the LLM, get and some error message, and then stick it back into the prompt and then continue, right? And this process would just go on. Okay, so this evaluation was done in 2024, actually late 2023. So, the world has changed since then, but at least at that point, we compared with GPT-4 and found that GPT-4 frequently gave incorrect errors, incorrect proofs. And by contrast, this feedback with the proof environment, Lean in this case, really helped for Copra. And so even though it was using the same underlying model, the interaction allowed it to create a correct proof in this case. Here are some experimental results. You can see the details in the paper, but in this picture on the x-axis, you see the number of queries, and on the y-axis, you see the number of theorems proved. So what we saw over here is that pretty quickly, the Copra approach was able to prove a lot of theorems with a relatively small number of queries, whereas the other approaches that didn't get that far. And here is an evaluation on mini F2F test. So the absolute numbers are not great, but then the amount of compute we provided Copra was also relatively small. We just allowed 60 queries per proof attempt. Now, what we saw here was that we got quite reasonable performance comparable with the state-of-the-art methods. Now, of course, since then, the state-of-the-art on this benchmark has moved quite a bit. So mini F2F, for those of you who don't know, is, by the way, it's a compilation of competition mathematics problems, mostly at the high school level. And so it's of the form that here is a theorem and come up with a lean proof. So here what we see is that there was this around 29% or 30% success rate, which is behind the current SOTA. But I think one question would be that if you take this approach and scale it up, then where would you end up? And there are no public results on that yet. So in this talk, though, I'm going to go beyond the method that we just presented, which is the basic Copra, and talk about some results that we just recently developed. This is not published yet. And here we are leveraging the ability of LLMs to abstract and also to use natural language reasoning. Because I think that this is really where the sort of approach that we just presented, this shines because of the tremendous amount of word knowledge that is stored inside LLMs. We can really use them in a lot more powerful capacity than just as a predictor of the next tactic. And so here's a sample problem. This is from IMO, and this is saying that, prove that this fraction is irreducible for every natural number n. So what we'll see is that the Copra approach can be extended a little bit to, in fact, come up with a hierarchical solution to this problem. And so this will involve breaking down the problem into subproblems and then solving hierarchically. Okay, so how do we do this? Well, first what we do is that we ask the LLM to come up with an informal solution to this problem. And so I don't know if this font is too small to read, but basically what is going on here is that this was fed to O3, a reasoning model, and so it was able to come up with this, step-by-step plan. So for example, you first define the GCD, and then you, subtract to simplify, then you apply the Euclidean algorithm, and then you conclude something about the GCD, and then you have the final conclusion. So then we say that, okay, so let's take this informal decomposition and put it in the context. Now, let's say that it's our goal to prove this lemma in Lean4, right? So this is the formal statement of the same problem. And we are just saying that don't try to write the proof. Okay, so let's just write the sub-goals that are needed to prove this. But we are doing this conditioned on the informal proof that we just generated. And so here is the proof of, or here is the decomposition of this lemma. So what you see is that it comes up with, these three sub-goals. So first you show that, this GCD step 1 is true. And it's basically saying that this GCD of 21n plus 4 times 14n plus 3 is the same as the GCD of this, 14n plus 3 times 7n plus 1. So then there is the second one, then there's the third one, and so on and so forth. And then finally, you have the main theorem that combines all of the above. So the appeal of this sort of decomposition is that now this very complex problem has been simplified into these three subproblems, which are a lot more tractable. So then in the next step, we then ask Copra to solve the subproblems one by one. And what we see is that Copra is in fact able to come up with these proofs of the subproblems. And here we are, here are the proofs. Again, I'm not going to go into the details of the proofs. This is something that you have to stare at for a little bit, and it's not actually especially complicated. But then once you have proven these lemmas, then you just put them all in the context, and then you also put in the informal proof, and then you ask Copra to prove the full theorem. And it is able to do that. But Copra is not able to prove this if you were giving it just this this entire theorem all as one block and just asked it to solve. So what we did here is really, something that is a highly powerful design pattern in LLM agents. LLM agents are extraordinarily flexible. So with just some variations on the ways you do prompting, you're able to make it do very, very different things that would take a tremendous amount of training if you weren't using these pre-trained models. And so what we did over here is that we started with a system that was just designed to be a step-by-step predictor of a low-level proof. And then we made it do high-level reasoning at this more abstract level, right? Because if you can think of these sub-goals as basically being abstractions of sub-problems. And so the LLM is able to create these abstractions, right? And once you have made use of these abstractions, your proof process becomes a lot simpler because now you're able to go hierarchically. And all of this was doable without any substantial training. You were just using the power of prompting, right? And to me, this is a huge revelation. The idea that you can use the power of language, the power of all of the stored knowledge inside LLMs, and then combine that with this sort of higher level algorithmics where you just put together the informal and formal reasoning steps in various ways, and change the prompting strategy, and you get something that is qualitatively different in capability. And now it turns out that the lean feedback here was also really important, because at least with O3 Mini, what we found is that there were hallucinated lemmas and so on. And the grounding that was provided by the lean theorem prover was absolutely critical to solve this problem. So now I want to talk a little bit about a different application of the same idea. This is in the context of formal system verification, which is one of the most practical applications of rigorous mathematical reasoning. And so what you're doing in formal verification is that you're mathematically modeling a real-world system as a set of definitions. And then you are modeling system properties as theorems involving these definitions, and then you're proving these theorems. These methods have led to extremely rigorous systems that are very difficult to, or almost impossible to hack. For example, there was this time in a program organized by the US Department of Defense, they used this formally verified Linux kernel called SEL4 to, and they put this on a drone, and then they got a red team to try to attack this drone for a period of 6 weeks. And they failed, right? Because the rigor provided by formal verification was just so much. Now, historically, formal verification has been extremely expensive. And as a result, its costs, it's not really been widely deployed because the costs are not justifiable except in the most safety critical scenarios. However, with the rise of AI, especially AI for math, the cost benefit equation changes quite drastically. And now you can imagine, doing not only proofs of math, but proofs of real world systems of, for example, correctness, security, performance, and so on, using this growing generation of AI tools. So here I'm going to show you a basic example of this idea. This can be scaled up substantially with more powerful models and more compute. But here, what we are going to do is to give you a very, very basic compiler and then show how to formally verify its correctness. Now, this is so simple, the compiler, that it's almost a joke. But trust me, when you go to more advanced compiler design, the fundamentals don't change. It's really the same sort of idea. It's just that there is more complexity. Now, okay, to do compiler verification, you would need the following pieces. So first of all, you would need to have a notion of a language. And a language consists of a syntax and a semantics. So syntax is a grammar that defines the form of the programs, and then semantics are the rules that define the executions of programs. And then a compiler is basically a set of rules that translate programs from one language to another. And then verifications is that you prove that the rules preserve semantics. So here we are going to talk about a very basic expression language in which you are allowed to do addition and multiplication. So this is just basic arithmetic expressions. And the syntax that you see over here, this is in a language called Coq. And here it looks a lot like Lean. It's similar, dependently typed functional programming language. And so what you're doing over here is that you're defining this binary operator. This can be either plus or times. You're defining this notion of an expression. And this is saying that it can be either a constant or a binary operation. And then there are some rules that tell you, how to actually evaluate these expressions. If you're given an expression, what will be the result when you evaluate it? And I'm not going to go into the rules in detail. I'll share the slides, and if you're interested, you can you can look up many resources on the web, but also I'm happy to answer questions over email offline, or actually after this talk. Okay, so then you define the source language. So here what you see is that you can define, the rules that we saw previously. They allow you to define the semantics of quite complex expressions. So here what you're seeing is that, you have const2. So an expression can be a constant or a binary operation, or the result of a binary operation. And you see that, this is the result of applying a binary operation to two expressions. And so this is a recursive definition, really. And then you are getting an expression as output. So here what you're seeing is that you can evaluate various complicated expressions in this way. And so now you have to define the target language, right? So this is a compiler is a mapping from a source language to a target language. So now you have to define the target language. And so what you did over here is that you are defining the target language as a list of instructions. So a program is a list of instructions. And an instruction is either this sort of a constant expression or a binary operation expression. So one way to see it is that while the original expression in the source language was defined in this recursive way, in the target language, when you are interpreting it, you are doing it using a stack. So this is a well-known idea in programming languages that if you have a recursive expression, let's say an arithmetic expression, then the way you can execute it is by maintaining a stack. And you can, keep pushing the current instruction on the stack, and you can basically do this kind of a low-level, build up a low-level machine, a stack machine. Actually, a lot of early computers were based on this idea. And then the stack basically, keeps pushing new things on it, and then you pop, and then you read the value that was just popped. So while very basic, it still captures a lot of important programming language concepts. Now, the point is that I want to believe that the mapping that I would do between these two representations is actually correct. But of course, first I have to define the compiler. And so this is the compiler. So what this says is that I am going to, take my input expression in the source language, and then I'm going to do a pattern matching. I'm going to consider these two cases, either when it's a constant or when it's a binary operation. And in each of these cases, I'm going to, generate a target language program. So in the target language program, the entire sequence of instructions is just written down as a list. Now it's when you are executing the program that you are maintaining a stack, right? That's when you are doing, all of the kind of modeling the recursion. But in the program itself, you are just doing this kind of you're generating the instructions from E2, you're generating the instructions from E1, and then you are sticking this B, and then you are just building up a stack with or a sequence of instructions with with all of this. So for example, if you started with this expression, b naught plus const 2 const 3, so this is 2 plus 3 that's really the expression. And so then in the lower level language, it's going to look like this. So then you have to define this correctness theorem, which says that for all E in the all programs, all expressions E in the source language, upon compiling this expression, you get something that when you execute it in the programming language's semantics, you get the same thing as if you evaluated the original expression in the source language's semantics, right? So these two are the same. Now, it turns out that Copra cannot prove this theorem just in one shot. So what you do instead is that you ask the LLM, again, think of the IMO example that I showed. This is quite similar. So you ask the LLM to invent a lemma, an intermediate goal. So the LLM goes ahead and thinks for a while, and this is O1 here, and it comes up with this intermediate lemma, which basically says that rather than trying to prove the entire compiler correct, what you instead do is that you just show one step of compilation, like for one sub-expression that's going to be correct. So basically that's the target theorem. The auxiliary lemma is saying that you can compile one instruction correctly first. And so this is really just simplifying the problem, breaking it down in a step-by-step way. And then we ask Copra to come up with a proof of this one instruction, and it's able to, which is fantastic. But then what we can do is just in the way we did previously, we stick this back, we take this proof, give it to the Copra agent, put it in the prompt, and then ask it to prove the entire theorem correct, and it's now able to do this. So that's what I have on this particular topic. In summary, I would say that mathematical discovery with LLM agents is extremely promising. I think that you can go a very long distance with just in-context learning, but you want to have the proof assistant feedback for proper grounding. And there is a lot of higher level agent design that you can do, where you can combine agents that are doing, for example, formalization with agents that are doing hierarchical planning, with agents that are doing low-level stuff, low-level proof generation. And this is a very new space. There is a lot to be done over here. Now, one question, again, going back to something we asked previously, can you get rid of this interaction by just pushing the whole thing to training? Maybe, you generate a lot of training data in this way by interaction with the prover, and then you just continue training the LLM with those traces, and then at some point the LLM just gets good enough. We are not there yet, but maybe this is a world that we can get to someday. But currently, we have to have these sorts of agent architectures. Now, there's this paper several of us recently wrote, and you may have seen a reference to this paper previously. Caillou is the lead author of this, and Don was the leader of the overall effort. But if you are curious about this area, you want to know more about specific challenges, roadmaps, then I would recommend that you go and look at this paper. I had a few things to say about open challenges, but I'm going to skip those in the interest of time. And I'm going to move on to the next topic, which is AI for scientific discovery, because I want to emphasize that this idea of LLM agents, this has a lot of value in this sort of deductive mathematics, where you are starting with a set of principles, set of axioms, definitions, and then you are proving statements in a step-by-step way. But it also has tremendous potential in empirical discovery, which is what happens in most of the natural sciences, where you are starting with data, and then you are trying to fit some hypotheses or some experimental claims or some claims to this data. Now we'll see that this is also a place where the abstraction abilities of LLMs play a potentially very interesting role. Okay, so very quickly, this is what a natural science process looks like. You choose a research question, you generate some hypotheses, you do an experimental setup, you collect some data, you do some analysis of the data, you interpret the data, and then you report to the community, right? And so just as an example of this, if you think of the world of astronomy, back in the day, there was this problem that was observed, which is that people believed that the Earth was the center of the solar system, but then some of the planets appeared to move backward. And so this led to this creation of this new hypothesis that, in fact, we have a heliocentric model. And then this led to the creation, the collection of more data. Tycho Brahe, in particular, observed Mars, and then came up with a whole bunch of precise measurements of the planet's positions. And then Kepler chose to analyze this data and then fit a wide variety of geometric shapes to this data. And then he came up with this Kepler's third law. And then this eventually led to Newton's law of gravitation. So there was this process that happened in science, which involved trading in abstractions, seeing some data and then coming up with this law in terms of abstract principles, but then further generalizing it into a law that was even more explanatory. So I think that LLM agents have tremendous potential in automating a lot of pieces of this pipeline. And in particular here, we are going to focus on the problem of symbolic regression, which is the task of coming up with equations based on empirical observations. So for example, an instance of that would be that if you were given these measurements of planet Mars, and then you wanted to discover Kepler's law, how do you do that, right, from the data? Now, one would think that LLMs would not be a great fit for this problem because the data is just really low level, right? This is just a bunch of numbers. However, it turns out that LLMs do have a tremendous potential over here in the sense that they can bring in prior scientific knowledge into the picture. What you have to do, though, is that you have to complement the use of LLMs with the use of other machinery that is able to, for example, evaluate hypotheses on the data and give you some notion of how well it performed. So once you have that kind of a mechanism for evaluating LLM-generated hypotheses, you can create an agentic loop where you have more and more feedback going to the LLM, and then this process of hypothesis generation is left to the LLM, whereas hypothesis evaluation is done by some other entity. And if you think of it, it's not fundamentally different from the way we use Lean or the proof assistant in the previous part of the lecture. So one of the most established approaches to symbolic regression is genetic programming. And here are some visualizations from a system called PySer, which is quite popular in this space. And so what's going on here is that you have a pool of candidate expressions, candidate equations being maintained. And then you have mutation and crossover operations being applied to those. And then you are updating this pool of expressions using feedback from a separate machinery that is evaluating these expressions and telling you, how good is the loss? How well does this match the reality that is there in the data? So this has had a lot of impact. There are applications in physics and other areas as well. And so here are some example papers. One thing that's interesting is that if you just imagine how does this process of genetic programming go on, so there is this pool of expressions that is being evolved. And so what you see is that there are these, islands of expressions. So these clusters, which contain expressions that are that have something in common between them. So the one way to think about how LLMs are relevant is that these clusters or islands of expressions, these capture various kinds of, various classes of functions. So for example, in this red one over here, you may have exponential functions. In this case, you may have trigonometric functions where you have the cosines. And so one way to imagine this is that an LLM looking at these expressions, because LLMs are good at coding and associating code with natural language, could perhaps come up with some explanation of what this piece of code, this expression is actually doing, right? And that's the idea of abstraction that we are going to use. Okay. So this paper was at NeurIPS last year and co-led by Arya Graeli, who was an undergrad at UT, and Atharva Sehgal, who's a PhD student at UT. And so the starting point here is that we want to do this kind of concept abstraction. And so what we want to be able to do is that we want to look at these variety of laws which come from very different contexts. But then we should be able to look at this and kind of tell that what's going on here is that you have this power law thing going on, right? And so the other thing we want to do is that we want to use background knowledge that was created by a physicist or that's there inside an LLM. So for example, here you have an LLM, a concept that has been produced, which is that wave strain diminishes as distance increases. This is the, let's say, property of the of black holes. And so you want to be able to associate this kind of information, this is a piece of common sense knowledge, to equations. So this equation, for example, satisfies these properties, but this is, you want to create a mapping between these two things. And because, if you imagine how the scientific process is ongoing, so let's say you have an AI that is predicting equations based on data, you also want it to be conditioned on this sort of high level knowledge that is being given by a human expert, right? And so you want to have this association between code, that is these equations, and language. So the way we set up this symbolic regression problem using LLMs is something like this, that we imagine that and actually here it's not just LLMs, it's more like a combination of LLMs and this sort of abstraction into high level concepts. And so we imagine that there is this universe of high level concepts. So for example, wave strain diminishes as distance increases, or power laws, or sinusoidal functions. These are sort of high level ideas that we have in our head. And there is a notion of a data set, which is the concrete data that you want to fit. And then you have a space of programmatic hypotheses. This is, for example, the landscape of equation, or the set of equations expressible in Python, or in some restricted DSL inside Python. And then what you're saying is that you want to jointly infer, given the data, this distribution over pi, which is likely hypothesis and likely concepts. So you don't want to just get likely programs given the data, which would be the goal of traditional symbolic regression, you want to get both the programs and also the kinds of concepts that they represent. Because ultimately, you want to explain these programs to a human scientist, or alternatively, maybe this joint distribution gives you more information than if you just operated in the program space. And so this you can factorize in this way, and then it turns out that the way to think about it is that P of d given pi is basically saying that if I have a particular program pi, what is the likelihood of the data? So how well does the program explain the data? In order to find this, you just execute the program, right, and see what kinds of results come out, and what the likelihood of the data set is. And P of pi given c is basically telling you that, okay, here are these here is a concept that I have. So let's say I'm thinking about power laws. Okay, so conditioned on this concept that I'm thinking about power laws, what is the probability of this program that this piece of code, right? To what extent does this piece of code represent a power law? And this is something that an LLM has background knowledge inside it to do. And then finally, I have this P of C, which is a prior over concepts. And this is also something that an LLM knows that, I have seen the literature of, let's say, physics until this point. So what is the likelihood of this concept, right? So all of this together gives you ultimately the ability to infer both a distribution over both programs and concepts. Now, in order to really implement this, this is the loop that we came up with. So this follows the basic structure of an evolutionary algorithm, but it does this sort of this sort of Bayesian concept learning thing guided by LLMs on top of that. And so operationally, the way to think about it is that you have like in any evolutionary algorithm, you're maintaining a population of hypotheses or programs. And then at this point, you have a choice of doing evolution either guided by the classical symbolic method, where you're doing some random tweaks to the abstract syntax tree of the program. Or alternatively, you are doing this LLM guided evolution, where you are saying that here is a concept, here is a program that I have, and I want to generate a new program. And when you are doing that, you are being guided by this concept library, which tells you that these are the concepts that I'm thinking about right now, right? So power laws seem really good, really well suited to this condition, this concept, or this setting, or maybe trigonometric functions seem especially well suited to this setting, and so on, right? So you are feeding all of that to this LLM guided evolution process, and that allows you to basically mutate the current programs into new programs. And then after you do that, you are, like in the usual evolutionary way, you are identifying the best candidates in this population. And so this is where you use the fitness function, which is how well does your hypothesis pool explain the data that you have, right? And this is where that P of d given pi that comes in. And so this is a little bit more detail about how the hypothesis evolution works. So you start with this initial program population, and then you're evaluating, you're getting the best program, you're mutating or crossing over, and then you're replacing the oldest program, and then this process just carries on for a while. So the important thing over here is that you're using the LLM for implementing this mutation and crossover operations. So in particular, rather than, in a classical genetic algorithm, what's going to happen is that you're given the AST and you're going to say that, okay, swap out this subtree by a different subtree. Now you're going to say that I'm going to ask the LLM to rewrite the program into something. And this idea was also used in the FunSearch paper from DeepMind last year. And FunSearch has been very successful. the way in which this laser work differs from FunSearch is fundamentally in its use of this concept library. But a lot of the other ideas are closely related. So this is just to highlight, the difference between the symbolic crossover versus the LLM crossover. So in this case, the LLM is basically doing all this. It's being given a crossover prompt, and then it's given some formatting instructions, and then it's generating the new expression. So after you do this, so you have evolved your hypothesis. So now you have this new pool, and now you also evolve your concept library. And so the concept library, this evolution process has these two stages. So first, you take your new programs that you've created, your new program pool, and now you're asking the LLM to abstract this into these sort of natural language, high-level descriptions. So for example, here, the LLM is telling you that, oh, this equation represents exponential growth or decay. And then the LLM, the concept evolution process is just like the hypothesis or program evolution process, except it now uses this, an LLM to basically combine, mash up these different concepts into a new concept. So for example, here you see that, exponential growth decay, this is one concept. Another concept says depends on temperature. And our LLM, because it has all this knowledge about all sorts of concepts relevant in physics, it comes up with this idea that, oh, this should be a Boltzmann distribution. This is a useful concept to have. And then this is going to influence the hypothesis evolution, which is going to influence concept abstraction and evolution, and this loop will continue. So one way to visualize this is that after the first phase, when you have done this hypothesis evolution, you may have these, islands of different kinds of expressions. Now, in the concept generation process, concept discovery process, you're going to get these, natural language descriptions of these different islands. So this is sinusoidal trends, this is power law trends, this is linear trends, this is exponential trends, and so on. And then what we found is that the use of this sort of a high-level concept library helped us in this equation discovery process. So we evaluated this on this task of equation discovery or discovering Feynman equations, just given the prompt that. So there was the data, but then there was a prompt that told you which chapter you were looking at, and so on. And so what we found is that this approach proved more effective than a version where you were just using either pure genetic programming or one where you were not using any kind of concept learning. And it turns out that even with local language models, when we didn't use a frontier model, we were still able to outperform this genetic programming approach. And the overall finding was that, and you can find more details in the paper, is that the use of this sort of high-level concepts generated by the LLM, it accelerates discovery. Now, one appeal of this sort of LLM-based approach is that it can very naturally take in user-provided hints. So in this case, we gave the algorithm some hints, which was, this is the kind of equation you are looking at. So in the previous experiments, actually, we did not have hints. So this was just, purely based on data. But then in this case, we had hints, and then we found that hints actually provided some benefits. So on the x-axis here, you have the number of iterations. On the y-axis, you have the, the fraction of equations solved. And then we found that the use of the hints, it provided a modest benefit, at least earlier on in the process. So here is an example of this in action. Here, this is the classic Coulomb's law. And then PySer is this genetic programming approach. And it gave this very unwieldy kind of expression that it turns out is equivalent to the ground truth expression. but it required a lot of simplification for you to, it would require a lot of simplification for you to go from here to the ground truth. Whereas the laser approach is able to basically, because of the uh, some of the knowledge that is there in the LLM, it's able to reduce to ground truth after 4 steps of simplification. Now you could say, wait a second, isn't the LLM cheating? Because it already has Coulomb's law in its mind. So how do you know that this is not just leakage? And of course, in this case, there is that possibility. But that said, I would say that the attraction here is that the input to the system is just this data, right? It's just the input-output values for that would result from Coulomb's law, and it's a very low-level kind of input. The fact that it was able to fit this to Coulomb's law is kind of interesting. But that said, we also did other experiments on synthetic data where you just manufactured a completely weird equation and a weird data set coming from that equation, and then asked the system to regenerate this. And we found that there were substantial benefits even in that case. So here is some information about some of the concepts that you ended up getting from laser. So you see there is stuff like, good mathematical expressions exhibit symmetry or regularity. But that said, there were also some expressions that were really, that didn't really seem to mean anything. But at the same time, there is no guarantee about the quality of the concepts. This is all natural language at this point. An interesting possibility is to use some kind of a formal language to describe the high-level concepts. Now, we also use this in a new discovery problem because we were also worried about the possibility of this being an artifact of leakage in case of standard benchmarks like discovering Feynman equations. And so we used this method to come up with a new scaling law for LLMs. And so here what you see is the so-called Chinchilla law. So this is a law that was postulated in a DeepMind paper from a few years back. And so here, basically what you're trying to do is to predict the loss of the LLM, based on these various hyperparameters. And so this was the law. So you postulate a scaling law, you measure model loss with respect to hyperparameters, and then you fit scaling law to data set. And in order to do this, of course, you would need to have a data set where you have a lot of values of these hyperparameters and corresponding accuracy values for the LLM. Now we did the same thing with laser. Rather than fitting a hand-fitted law, which was done in the Chinchilla paper, right? So they basically postulated a law like this, and then they fit the parameters. But by contrast, what we did is that we just asked Laser to go find it. And Laser was able to come up with this sort of a law where we also had this parameter called number of shots, which is that if you're doing prediction, what is the number of examples that you're giving it in context. And this parameter is available in some of these data sets, right? And so what we found is that there was this interesting kind of law that came up. Now, this is just one example. It's not really very comprehensive yet, but this just shows that you can make these kinds of new discoveries using this law. And so basically, if you interpret this, the way to think about it is that a large number of shots gives poor results for low capability models. But then once the models pass a capability threshold, then having more shots helps, right? And this is sort of a common sense linguistic interpretation of the law that came out. So, you can also do something after this. So if you're thinking of yourself as an LLM scaling law person, you start with the Chinchilla law from the previous paper, and then you say, okay, maybe I should bring in this insight about shots into the Chinchilla law, combine the old Chinchilla law with this new discovery that was made by Laser, and then you find that this modified Chinchilla actually is able to do better than both the old Chinchilla and also the Laser itself. And so this is kind of interesting that and shows that this discovery process using LLM agents, and this is very much an agent, right? This is not just a one-shot LLM. You're using an LLM combined with this various other tools. So what you are getting out of this is can influence human discovery as well and lead to something that is greater than the sum of the parts. So in the interest of time, I'm going to skip this next bit. But what I said there is that these ideas can also be applied to settings where you have visual high dimensional inputs, because now we have vision language models as well. So you can go crazy and build these kinds of evolution-based agents where you have VLMs as part of the story. And I'm extremely optimistic about this direction. So in summary, I would say that LLM-directed evolution is a powerful tool for empirical science. And this point has already been made previously by FunSearch, but now we see that we can make it even more powerful with these ideas of abstraction that are that LLMs can give you basically for free. And even this can be even extended to visual settings where you have to use now vision language models, but hey, they're coming a long way. They have come a long way. And importantly, the abstraction abilities of LLMs can also be really helpful here. Open challenges, verification of hypotheses and concepts, concept representations that go beyond natural language, scaling to larger search spaces, input dimensions, and then even going beyond hypothesis generation to other parts of the scientific discovery process. But at the end, though, I am very optimistic that LLM agents, not just LLMs, but these kinds of agentic workflows where you have combinations of LLM queries as well as other kinds of machinery, they can be extremely powerful in scientific discovery. They can help you come up with new scientific hypotheses and even do experiment design. And also, as we saw in mathematical discovery, they can be supremely powerful. And again, we are just in the early stages of what I think this line of research will end up being. And this can have applications in math, in science, in engineering, as you saw, the formal verification application, building rigorous systems. So the future is very bright. And with that, I'll end. I want to thank all my collaborators and funders. And I'm happy to take questions.